Today I'm discussing the inverse of a square matrix. Let's start by understanding what an inverse matrix means. Suppose we have two matrices named A and B such that when A is multiplied by B and B is multiplied by A, the result in both cases is the identity matrix, which is a special kind of matrix that acts like the number 1 in matrix multiplication. If we define another matrix Z such that when Z is multiplied by A or A by Z, the result is also the identity matrix, then Z is uniquely defined by this property. You can verify this considering that if you have another matrix D that behaves like Z, then multiplying D before or after A should give you the identity matrix. Since both products give the identity matrix, we can conclude that Z and D must actually be the same matrix. This shows that the inverse of a matrix, if it is unique. Furthermore, a product of two matrices, say UMN and A, is invertible if there is a matrix such that C times A and A times C both result in the identity matrix. This is a crucial property because it indicates that matrix C is the inverse of A. If a matrix is not invertible, it is referred to as singular. An important point to note is that every elementary matrix is invertible. This follows from the rule that the inverse of a product of invertible matrices is the product of their inverse in reverse order. For example, if A and B are invertible matrices, then their product AB is also invertible, and the inverse of AB is the inverse of B followed by the inverse of A. Now, let's consider the process of finding the inverse of a matrix using elementary row operation. If you can reduce a matrix A to the identity matrix using this operation, then the matrix you use to perform this transformation is the inverse of A. If this reduction isn't possible, then the inverse does not exist. For example, if you start with a matrix A, you might use operation like swapping rows or scaling them to simplify A. Your goal is to transform to the left side of the augmented matrix, which starts as A next to an identity matrix into the identity matrix itself. As you apply this operation, you simultaneously transform the right side of the augmented matrix into what becomes the inverse of A. This approach shows how using elementary row operation is essential for manipulating matrices and finding inverses, enhancing our understanding and ability to solve linear systems effectively.